what we're going to do, we're going to pick up from where we left off yesterday for the first period. Okay, the second period again today is going to be time for your prop sets. We're not at the point on the next lab yet. We'll be there.
We don't have this double.
We do have a double today, guys.
Yeah, we have double today, but we don't have class tomorrow.
Yeah, but there's no class tomorrow. Sure. Today's your double. Test is Tuesday. That's Tuesday.
The test is Tuesday. Wait,
So-
it's Tuesday?
Yes, it's Tuesday.
Today's?
Officer.
Guys, focus.
Monday.
Stop. Come on. We talked about all this yesterday already. We need to do it again.
Officer or Monday.
Today. All right. So yesterday we left off with normal force. We talked about real quickly how the normal force is usually, and I mean usually, opposite the weight of the object. This is what holds the object on the surface. Now, we're going to do an example in a minute that demonstrates that the normal force is not always the exact opposite value of the weight. If you have a simple object resting on a surface, like this water bottle here, then the normal force is acting straight up with the exact same weight as the water bottle. But in the case where we don't have that, what if we have this water bottle here, and I start to try and lift it up a little bit, and I pull up on it a little bit, but it doesn't lift off the surface. Well, now the weight feels like it's less. And you've done this before. If you've ever tried it, if you ever stand on like a scale and you want to weigh yourself, if you push up on like a counter, you'll notice that your weight goes down. Because the scale measures the normal force. That's what a scale does. So every time, that's if you lift up.
Oh, yeah.
So again, you're on a scale. If you push up on a surface to push your body upward, it's like you're weighing less. So you'll see the scale go down because it measures the normal force. That's exactly what a scale measures, normal force. Now, if you're standing on the scale and then you try to lift something, it's going to include it in your body weight, so your weight's going to go up a lot. So depending on what you do, it will change whether your body weight goes up or down. Now, we talked about this yesterday. Let's get into an example now. So here's our example for today. If an object is at rest on a table, and the object's mass is 10 kilograms, and you're trying to lift it with an upward force of 35 newtons, will it lift off the table? That's our first question. Will it lift off the table? If not, if it still is on the table, what is the normal force exerted by the table? Take a second to write it down.
Wait, so will it lift off? And then what's it if not?
If not, what is the normal force exerted by the table? Bless you. And let's think about this logically for a second. God bless you. Normal force only exists if the object stays on the table. If you lift it off the table, there's no longer a normal force. Because remember, normal force is a reaction. So, if I have, and I'll erase this in a minute. Say I have a crate on the floor. The mass or the weight of the crate acts straight down, Fg. The normal force acts straight up, Fn. Now, if you lift the crate off the table with your hands, the normal force does not exist anymore. Because the normal force is a reaction to the weight. But if you use your muscles instead of the table to actually hold that object, it's not going to need a normal force anymore. So the minute I lift this water bottle off the table is no longer exerting a force, which is obvious because there's no connection here, right?
Yeah.
And this is normal force is a contact force. You need to have contact. Whereas we talked about the field forces that can act at a distance. This is in contact right now. It's pushing back up. I lift the water bottle off the table. It's no longer in contact. There is no normal force on the water bottle anymore. So for this problem, we need to figure out first, with a force of 35 newtons upward, will that overcome the weight of the object? If it does, then you're done with the problem. If not, then we want to figure out what is the normal force that's left over to compensate for what's left over when you try and lift. And what I'm saying is this. If I take this water bottle and I try with one finger and I try very lightly just to lift it off the table, it's not going to go anywhere, right? But I am putting some force upward on this. So let's say I'm applying a force upward of like a half a pound. But this object, let's say it weighs about 2 pounds maybe, 32 ounces of water. So it weighs about 2 pounds, let's say. If I push up with a force of 1 pound, it's not going to lift it off the table, but it is lightening the load on the table a little bit. It's making it easier for the table to support this object because I'm helping it. I'm pulling half the weight up, but it's not moving still until I pull the full weight up and then it starts to lift off. So I can sit here and continue to pull harder and harder upward. Nothing happens until I break that weight and then it'll move off the table. So the normal force is going to change based on how much I pull upward on this bottom. And that's what we're going to look at now. So first, we're given the mass of the object. We're told that there's a certain amount of force exerted upward, and we know that every object has a weight. So if I want to draw one more thing on my diagram, I need to consider that force I drew upward. So how would I do that on this diagram? Force of 35 newtons. What would it look like? Just look at your directional.
You mean
Before we get to equations,
If you're
we need to include that force.
Then the 35 means you're going up.
Good. So where would you put it though, Max? Would you show it from the top, the bottom, left, right?
You do the top right, or like the top somewhere.
Yeah, I would just do the top somewhere. Just traditionally, guys, I would use the top middle, okay? When you have an applied force, just draw it like that. And we'll call this Fy.
Then isn't there like 35 means going somewhere else there?
But that is the 35 newtons, Fy.
Then there's another, isn't there? It's like the opposite.
Yeah, it's the negative 9.
Isn't there then 35 means
Well,
going
that-
onto the?
That's what we're gonna discuss now. We're gonna see how that works with the weight of the object. Okay? For now, all we're doing is drawing a free body. We're not drawing. You're thinking of a force diagram where you draw the reactions and everything.
Yeah.
This is a free body diagram. The only thing that is acting on this, object? On this object is the person pulling up with Fy, the weight of the object pushing down into the table, Fg, and then the normal force supporting it on the table as well. There's nothing left and right. The object is not being slid to the left or the right, so we have nothing in the x direction. Okay? Now, Jeff, what did you say? What are we going to use? What rule? What equation?
F equals MA.
Good. Now, we're only in the y direction, so let's write it like this, please. Fy equals MAY to indicate that we're working in the vertical direction. So the sum of the forces in the vertical direction, you could put a summation symbol. But I told you guys I dropped that symbol a lot, but it means sum. And sum means add up all the forces. The sum of the forces in the vertical direction equals the mass times the acceleration in the vertical direction. Now, before we can use this equation, we have to think logically. You're only going to have acceleration if the object moves, right? Like if I pull up on this water bottle and it's not moving, is it accelerating anywhere? It's not. But the minute I do this, it starts to accelerate, right? Moving up and down. So we need to first decide, is the force upward going to overcome the weight of the object? If it does, then we can figure out that there's an acceleration. If not, then there's no acceleration, and then we have to look at the normal force. So tell me, how can I figure out the weight of this object?
So why do you need to add up forces? You just need 35. That's all you have. You don't have any.
Look at all of you have weight acting down, you have the push acting up, and then you have the normal force acting up.
Yeah,
You have three
You
forces.
don't know the other two.
That's what we're going to figure out. So what is the weight? How would we figure out the weight for this one, man?
Like you have to figure out how much you need to push upwards for the sum, and that would sort of estimate like the weight.
Okay, but you have the mass, so tell me formula-wise, what would you use from yesterday? How do we calculate weight? Remember yesterday's formula? You want Fg?
Wait a second.
FG
Half
was
FG, the absolute value of
Mg, right? So Fg equals mg. Remember, the weight of an object is its mass times the gravitational constant. We don't need the negative for g. We did that yesterday because we have this arrow pointing down, which already tells us it's going to be a negative force. So let's write down Fg equals m times g. Jeff, relax, please. Distracting me. Fg equals 10 times 9.81. Just put it away, please. So, what do we get when we multiply 10 by 9.81? Just move the decimal over. Good, 98.1. So the weight of this object is 98.1 newtons. Now, I'm not going to put a negative sign yet, because I only apply the negative sign when I look at the sum of the forces, because that's when the direction matters. But if I think about this now, if the weight is 98.1, the weight acting down, and you're pulling up with 35 newtons, you're pulling up with 35 newtons, which was given, is the object going to lift off the table? Why not?
Is that Fy or Fg?
Fy, Fy, Fg, Fg, Fg.
Why do you substitute G for A? Because it's gravity? G stands for gravity? Or
Look at your notes from yesterday. We talked about the weight being Fg equals mg. It's in your notes, Jeff.
And then,
Jeff. good. So again, the force pulling upward is 35 newtons. The weight of the object is 98.1. So the force does not overcome the weight. So this object will not lift off the table. That's our first step right here. If the object doesn't lift off the table, it's not moving, right? It's not moving. So what would the acceleration be, Molly?
0.
0. Is that what you're going to say?
Yeah, no, I was just asking,
Right.
the force of the newtons, it would have to be 98.1 or greater.
Exactly. If Fy, the applied force on this object, your arm, was greater than 98.1, it would lift off. If it was 98.1, actually, it would still stay still. It would be an equilibrium state, okay? But there would be then no normal force. We'll talk about how that works. So again, this object is currently at rest. So let's write this to be 0 now. Again, how come I can do that? Because mass times 0 is still going to be 0. And what we've shown right now, by solving for this value, we've seen that this value is greater than the applied force. Therefore, the object doesn't lift off the table, so acceleration is now 0. Once you've done that, you can then start looking at your sum of the forces. Before doing that, though, you don't know what to set it equal to, whether you should have MA or 0 over here. It depends on the problem. So let's take a look now. If I want to sum all the forces, and I'm saying again, sum of the forces in the y direction equals 0. Sum of the forces in the y direction is equal to 0. What are the forces acting down? Or what is the force acting down? Gravity, good. So we write negative Fg, because it's acting down. So this is why I kept telling you guys yesterday, when we look at forces, you don't have to think about G as negative 9.81, because we're going to put the sign on there anyway, because of our vector that's pointing downward. Because this arrow is pointing downward. What forces act up? What forces act upward? Mash? The normal and? Very good, the applied force. And altogether, the sum of these is going to be 0 because we are in a state of equilibrium. The object is not moving off the table. There is no acceleration, so normally if there was acceleration, you would write equals ma. But because this object is not being actually moved off the table, there is nothing on the right side of the equation here. Next, why do you look a little disturbed?
Can you just explain the FN part, like just like, so you know it's 0, but how would you ever ask us to find FN and like Fy?
Yeah, what we're going to do now is find the value of Fn.
But you already know it's 0.
No. The overall, guys, all of your forces added together equals mass times acceleration. That's Newton's second law. If the object isn't being lifted off the table, there is no acceleration. So instead of this saying ma over here, we just put a 0 over here, because acceleration is 0, because it's not moving.
Oh, those, okay, yeah.
This is the sum of the forces.
That's Fy.
Okay.
Okay.
This whole thing here is the sum of the forces in the y direction, yes. Okay? The gravitational force acting down is negative 98.1 newtons. The normal force is what we're searching for. The force applied is 35 newtons, and that equals 0. Again, gravitational force is negative 98.1. That's the weight of the object acting down, thus the negative sign. The normal force pushes back up, but remember, the normal force doesn't need to do all the work anymore, because I'm also helping it by putting 35 upward. Again, in this problem here, the weight acts down, but the normal force does not need to help me the whole way, because I'm also pulling upward a little bit. So imagine it's like saying here, all right, see this desk here or this cabinet? If I wanted to lift this cabinet myself, I would have to lift it with however much weight it is, right? Say it's 100 pounds. I don't know what it is. You'd have to lift up with 100 pounds. But if Paul walked over and he said, you know what, I can apply 70 pounds of force. How much do I have left to pull? 25, right? So 75 for Paul, pulling upward, and it weighs 100. I only have to compensate for 25. That's what's happening here. The table normally has to push back up with 98.1 newtons to counteract the weight. But because I'm putting in 35, the table's going to put in some value a little bit less than that. Okay? So if we solve for Fn, move things around, solve for Fn, what do we get here, Vivian? Positive, right? 63.1? Because you got a negative on the left side, then move it over. Right, move it on over. Okay? And this makes sense because, again, normally the table needs to provide a full 98.1 newtons. But because I'm helping with 35 newtons, it only has to provide the difference there, whatever's left over. So the normal force in this problem is not the opposite of the weight because I started helping you with a force up. Jack?
I'm just confused as to why Fy equals 0, the sum of Fy equals 0.
This is our normal equation at the top.
Yeah.
Once we realize that the weight was 98.1, we know that if the force acting down is more than the force acting up, it's going to stay on the table.
Yeah.
If this 35 were a number like 120, it would remove it off the table. So there would be some sort of movement or acceleration. But because the weight is greater than the normal force, it's staying on the table, it's not moving, there's no acceleration, so we drop that off. It becomes 0.
So then but how come we plugged in 35N for down there?
Okay,
That's 'cause
so
we're
this
using-
right here means sum of all the forces.
Yeah.
So we have to look at our force diagram, or our free body diagram, and look, we have 1, 2, 3 forces.
Yeah.
So that's what we did down here now. We went down further and said, well, the sum of the forces equals 0. That's right here. Then we said we have the weight acting down, we have the person pulling up with 35, and then the normal force compensating for the rest,
Okay.
acting upward.
Okay.
That's why those are positives and the weight is negative.
Okay. Thank
Jack?
The table isn't exerting a force upward without the bottom, right?
Correct.
It's all over.
Correct.
So what is the table is exerting nothing normally when there's nothing?
Correct.
Okay.
The floor is exerting force on the table, and if there's nothing on the table has no normal force to do, no normal force to actually happen. And then you put an object on there, though, there is normal force. Okay? Again, until I do this. Until I pull up with enough force, then let's go off the table. Molly? Paul?
How does the FG become negative?
All we look at on our free body diagram, Paul, is the direction of the arrows. The weight acts down, right? So it's negative. So that's why I said yesterday, don't worry about the negative for the 9.81, because the downward arrow indicates to put a negative next to that force.
If I
Okay.
were to think through logically, I would think that the force of the water bottle is going down, and then the table is exerting it back up against it.
Exactly. And the force of the water bottle is Fg going down, plus negative, and then Fn is the table pushing back up, and that's why Fn was positive.
Wait,
You said it exactly right.
maybe then I'm confused because I was thinking that
Go ahead. I'm listening.
the force of the object would be going against the table down.
That's right here, negative Fg. That's that. That's the force of the object. It's
I
its
thought
weight.
that was the force of the table here.
Negative Fg is the weight of the object. Fn is positive in the middle here. That's the table. Okay?
Except on the diagram up there, you have the arrows against Fy, 35 newtons going up.
Up. Is that the applied force? No. That's the applied force. Fy.
Yeah, okay, then we doesn't need to look at this.
Because the y's and the g's look similar. Don't confuse them. Again, g is acting down. Always down. Okay? Let's do another one because that seems to be a little bit confusing. Well, actually, let me ask a follow-up question. If I were lifting up with a force of exactly 98.1 newtons, what would change about this problem? Olivia?
Well, there would be no normal force.
Yeah.
You've already applied all the way that's
Very good. So this number here, this is our force applied upward, would change to 98.1 if I did that. And then wouldn't those just cancel? And you would get Fn equals 0. Okay? Which is saying that like I'm pretty much suspending this right on the edge of the table, like that, right there. So the table's not providing any force, but I'm holding it right there, and it's not moving. The minute I start to do this, then it's going to accelerate upward. But it's currently in equilibrium. The table's not helping. I'm supplying all the force. Then I let go a little bit. The normal force starts acting up until I let go completely. Then the normal force acts up completely. Okay? So the normal force can change depending on the scenario. It's not always going to be the equal and opposite of the weight of the object. Okay? All right, let's say we have, I'm going to make up this example because I want to do one more before we go on. we've got two objects stacked on top of one another. The upper object has a mass of 5 kilograms. The second object has a mass of 15 kilograms. I know both masses now.
I guess there's two
Two objects stacked on top of one another. Now, here's my question for you. Find the normal force from the table and find the normal force from the lower object on the upper object.
So the table to the ground, or that object to the same.
So again, I want to know what is the normal force acting up from the ground. And then we have another normal force, we can call that 1 or 2, it doesn't matter for this case, 1. Then we have another normal force which is provided from the lower box to the upper box. And think about this logically. Right now the table's holding on my water bottle. If I stack this cup on top, now the table's holding up both of them and the bottle is also holding up the cup. Okay, so use the logic right now. Okay, it's holding this, now it's holding both, and the bottle's also holding the remote. So that's what we have going on here.
So
Now-
just the total of the normal force from the table to the upper top.
We could try that, yeah, but I want to break it into little individual objects.
Is that a 7, or like the 420 or a 9?
Fn1, Fn2.
Oh, no, right.
That's a right angle.
Okay, yeah.
Right angle, yeah, so, what is keeping these objects down on the earth? Gravity. That's keeping it supported. What's keeping it down? Is it down? Gravity. So let's also draw Fg1, or in this case, sorry, this is Fg2 because this is mass 2. And this is Fg1 because that's mass 1. There's a lot going on here. Okay? Each object has its own mass, therefore each object exerts a force downward. I want to draw the free body diagram of these objects individually. Okay? So, first, let's draw the smaller object on top. Then we'll draw the larger object on the bottom over here. The smaller object up top, what's happening to it right now? What forces are acting on the smaller object up top? Gravity pulling down, and that is Fg1, and the normal force pushing up, which we happen to call Fn2. The subscripts don't really matter. Just keep them as long as you're consistent. Okay? So that's the smaller object up top. That's what's happening. We all agree with that?
Yeah.
Yeah? Okay.
Wait, I thought, sorry, we had to keep the numbers consistent. Why is the bottom one Fg1 and the second?
I meant consistent with the original diagram. Sorry, that was one another. Yeah. I called this 1 and 2 because I was thinking this is the larger one and this is the smaller one.
Okay.
It doesn't really matter. Larger object now, a little bit tougher. First, what's always acting to hold it down on the ground again? Gravity. What's keeping it up on the table? What's pushing back up? Good, normal force. We'll call that Fn1. Now, there's something else going on here. Go ahead, Mom.
It's holding up something.
It's holding up something.
It's getting pushed down on.
Yeah, thank you. Very good. Think about it. If I sat down, or if you laid down on your stomach on the floor, and somebody walked over you, you would feel them pushing down on you, literally, right? You'd feel their feet stepping on you every time. That's what's happening here. So what we have going on right now is there's really an applied force. The applied force is acting down on this object, and just to be, I'm going to draw it in the middle. I'm going to move this label over a little. The applied force is acting down. The applied force is acting down on this object. What is the magnitude, or what is the value of that applied force?
It's not 5.
Sasha, it's not 5.
The negative of the normal force first.
Close. You're on the right track first.
49.
Go again. So what is it physically? Tell me. It's the what of the box? Thank you. The weight of the upper box is pushing down. So here, what we can actually write is Fg1, because that's what the weight of the upper box is, right? just to be consistent with our labeling. Is that clear so far? Again, if you have an object and you stack another object on top of it, the weight of the upper object pushes down on the lower object.
Wait, so the 49, when you put it in the
Yeah, where are you going
FG, I don't see where you go. Wait, okay, so.
You need to ask questions one at a time, because I can't answer all of you at once. Gary.
Where did we get 49 point,
They're doing 5 times 9.81. The mass is 5. Remember, guys, this is, look, 5 times 9.81. You're all forgetting to multiply. This is 5 times 9.81. This down here is 15 times 9.81.
Wait, but what's the difference between FG1 and FG2?
One is the first object, one is the second object.
But, because we're just showing them all.
This is the smaller object, its mass is 5. It's acting also down on the upper object, and the upper object, its own mass is acting down. Jeff?
Okay, so when we use the negative FG plus FN plus
It changes. Forget that problem. That problem doesn't exist anymore, Jeff. Every problem is different in this. That's the thing. All you know is sum of the force equals Mn. That's it. From there, you identify and isolate all the forces.
so wait, so
that's the box on there.
sum of the force equal MN.
Yes. Masha?
How's our acceleration if it's not moving?
Well, that's the thing. For this problem, there's not going to be acceleration. So we're going to set it equal to 0 because it's an equilibrium. Okay? So again, we start with our equations. Let's take a look. We want to write sum of the forces for both objects. So for the small object, what are the forces acting on the small object? Give me negatives and positives also, please. The smaller object, what's acting down on it? Jeff? Gravity, good. So negative Fg1. What's acting up, Jeff, on the small object?
No reaction with the second and first object.
Good, and we call that Fn2, right? Fn2. So again, everybody, take a look. What we are doing is literally just writing out what we see in this diagram right here. We see the weight is acting down right here. We see the normal force is acting up. That's why the signs are the way they are. Now, are these objects moving? So is there acceleration? So this equals 0. That's the first equation for this problem. Now we look at the other object. Now we look at the other object, the bigger one. What's acting downward? What's acting downward? If we look at the diagram, literally look at the diagram, what arrows face down, Paul?
The FG1.
Good.
And the FG2.
Good. So in this problem now, for this one, and I'm going to do that, I'm going to do it over here just so you can see. We have negative Fg1 pushing down on the top of the box. We have the weight of the actual box also pulling it down. What's pushing back up?
The normal force for the second box.
Yes, we called that Fn1, right? We called that, if you go back to our diagrams to be consistent, we called that Fn1 right here.
The negative FG2 is the weight.
Negative Fg2 is the weight of the big box right here. Negative Fg1 is the weight of the smaller box up here.
And then do you add gravity?
Did you add gravity? What do you mean?
Gravity going against it as well.
This is gravity. Weight is gravity. Weight is force due to gravity.
Yeah.
The object's not moving, so we're not thinking about acceleration. There's no movement. So this is where gravity is taken into account. Now, since it's not moving, we set it equal to 0. Okay. In the first one, on the left-hand side, we know what Fg1 is. We know, Daniel, sorry.
Sorry, why is the first one negative FG1? That's just because it's not.
Over here, because there's an object on top of this object acting down on it. Right up here. See this right here? This object, this Fg1 right here, is pushing down on the box. The weight is also pulling down, so those are both negatives, and that's why you see them both as negatives here. On the left-hand side, if I want to know what the weight of the upper object is, I take its mass times 9.81. So let's go ahead and do that. 49 point. So if I were to move it over, what does it become? It becomes what? Positive. And that makes sense because Fn2 is acting which way, guys? Up. Now, before I take questions on that, let's get the other answer and we'll see what the difference is here. So that's the normal force acting up on the smaller block. Now, we then want to find the normal force acting on the larger block from the floor. I know these two values, so let's plug them in. Negative 49.05 is Fg1 because we knew that from right here. Remember, it's the same value as it was over there. What is negative Fg2 going to give me? Joey.
147.15.
Thank you. Now, how'd you get that, Joe?
I took its mass and I multiplied it by the gravity.
Very good, sir. So 15 times 9.81 gave us the negative 147.15. So if I want to find the normal force from the table, what is it really just a matter of? You're adding these numbers together, really, right? Because if you move these both over here, wouldn't you add them to the right side? So just add these two values. When I add them, Joe, what do we get when we add these two?
Thanks, Joe. Sound very white today.
196.2? Okay. And this is logically correct. And think about it for a second. So, this chair is on this table. Okay? So the table supplies the normal force back up on the chair. Now, I then put the water bottle on top of the chair. The table is now supporting both, correct?
Yeah.
So if the chair weighs 5 pounds and the water bottle weighs 2, what is it supporting? 7. Just, not 10. 5 and 2. So if it's 5 and 2, if it's 5 and 2, we add those together. Same thing here. The table is holding up both boxes. So it's 196.2, which is just the sum of both of those weights. But the chair is only holding the water bottle, right?
Yeah.
So what's the chair's normal force?
2.
Just 2. Very good, Mom. Again, the chair's normal force pushing up on this water bottle is simply 2. That's this answer over here, really. The lower box is supplying a force of 49.05 upward to the upper box. Okay, to the upper box. Questions so far? Questions so far? Masha?
Why is the first one in Newton and the second in State?
Oh, they're both Newtons. They're both Newtons. That's an M. Sorry, it's just me being very sloppy. Force is always Newton. Sorry.
You don't need to add them though? Together to find the total.
Well, remember, this is. Let's go back to our diagram. Okay, let's go back to the very beginning. Fn1, we got 186.2. That's what the table's pushing back up with.
Yeah.
And then 49.05 was what we got for Fn2. That's what the lower box is pushing up with. So we were just asked to find each normal force individually. Okay?
Alright.
Jeff,
What was the actual question in the end?
what was the actual question?
Yeah, like what was
Find the normal force provided by the table. Find the normal force provided by the lower box on the upper box. Okay?
And the normal force is just always the weight, or at least for the second object.
It might be the weight, the normal force, but if there's other things acting on it, it changes. Like we talked about earlier, where if I lift this bottle a little bit, it's no longer the weight because it goes down. Yeah. Let's do another one of these examples. What if we have an object on rest, God bless you, with a mass. Let's say the mass of the object is 8 kilograms. I walk over to the object and try to lift it up with an applied force. By the way, if you want to call this FP, your book does that from time to time, like the force of a push or pull, because that's what you'd be doing, right? You'd be pulling on the object upwards. So we can call this force the applied force FP also. You're going to see there's different nomenclature, okay? So let's say my applied force is 100 newtons. 100 newtons upward. The question to you is this again. A, will the object move off the table? If so, what's the acceleration? If not, what's the normal force? Again, will the object move off the table? If it does move off the table, what's the acceleration? If it doesn't move off the table, what's the normal force the table is providing? Now,
I don't think it goes off the table because FG equals 78.48. No.
keep going on.
I did 8 times.
FG equals 8 times 9.81.
That's what I did.
Go ahead, Lonnie.
Oh.
Yeah, you're practicing. All right.
Oh my gosh. Okay, so you get 78.48.
So the weight of the object, so what is it?
So it does.
How come this object will move, people?
Because it's pulling up more than it weighs.
Exactly. If you lift an object, if you put a force on this table with more than the weight of the table, it's going to move, right? It's definitely going to move. Now, if it does move, the question now becomes, what acceleration does it have now? So we have to go back to our equation. Jeff, what's our equation again? You started us with today. F equals ma. Oops. So we've got I don't need to draw the normal force in my FBD because I know that my force of 100 exceeds the weight. So all you need to do is this. And that's our sum of the forces. That's it. So again, sum of the forces, and we'll put the y direction, okay? Just to be clear. Sum of the forces in the y equals mass times the acceleration in the y. Now, sum of the forces in the y, we have Fp acting up. We have, hold on, Fg acting down. That equals MAY. We don't put 0 anymore because Fp was bigger than the weight. Plugging in, we put in 100 minus 78.4 equals 8 times the acceleration. Where's the 8 coming from? Is the mass of the object. The 8 is the mass of the object.
What was 100?
100 was the force applied upward.
Okay, right.
And the weight of it was 78.4. Okay? So we get a difference of, looks like 21.6 equals 8 AY. Divide by 8 on both sides, you get 2 point what?
7.
Thank you. And my units are meters per second squared. My acceleration is positive because the object is moving up. 21.6. 21.6.
And then this, you got 9A, 9Y.
No, this is A sub y. It's just the board is way off in the corners, guys. The calibration's off. A sub y, the acceleration of the object, once it's lifted, turns out to be 2.7. Go take a break for about 4 or 5 minutes. Get your textbook if you don't have it already, so you can work on those problem set questions.